Okay, good morning to all of you. Today we will be discussing about one small topics concerned with the energetics and the BMR. Now, one of the important things which we should understand here is that the ATP is one of the most important substance in the cells which is providing energy for all the activities which are going on, that is the cellular processes going on. So that is why it is called as the currency of the cell, where as long as ATP is there, breaking down of this ATP is generating certain energy, high phosphate energies, and once this high phosphate energy is generated, some energy is released and that energy is utilized for the cellular activity. So briefly, if you see here the slide there, you will find that what is the use of ATP by various cells and various organs. Now, nearly in the first place, all the cells have got certain chemical activities, that is the biochemical activities going on, where there is an oxidation of foods taking place, that is the basic foodstuffs, carbohydrates, fats and proteins. These are forming bonds, and for the formation of these bonds, you will notice that there is a requirement of the high energy phosphate bond. So for all synthetic reactions which are taking place, you will find that there is a need for energy, and this energy is supplied by the ATP generated in the cells. This is at the basic cellular level and in each of the cell which is present in the body. The other structure which is actively utilizing the energy is utilizing the ATP and producing energy is the muscle contractions. We know that there is an actin myosin cross bridge formation taking place. When there is a sliding going on, certain contractions takes place. When the muscle contractions takes place, it utilizes energy. In fact, it is both an active and a passive process, where contractions and relaxations utilize energy, and this energy is provided by the ATP which is present there in the muscle cells. So it may be the ATP or it may be any other form of energy, but the basic source comes from ATP. And even when the muscle is not contracting, say for example you are at resting condition or you are just standing, there are certain anti-gravity muscles which are having a contractions or keeping your body steady, standing up against the gravity. So when you are sitting, keeping the back muscles, keeping the position erect. So in such situations also, though there may not be any physical movement taking place, but there is a sustained contraction which is going on, and that also would require certain energy. Then active transport across all the membranes. Now this active transport, apart from the cellular level, is actively happening in the kidneys. The kidneys, you will see that there is active transport of substances, that is electrolytes, which is going on across the tubular membrane. In the GIT, there is an active transport of substances going on. Even at the cellular level, you will find that substances are going in and out, whether it is nutrients or it is micro elements or trace elements. All this will require certain transport across the gradient. When a substance is being transported across the gradient, it is an active transport and it requires energy. And once that is done, you will also require it to come back to normal. That is, the electrolytes which have been disturbed has to be brought back to normal. Again, that will require the ATP form. So in active transport across the membranes, we require energy, and that energy is supplied by ATP. Maximally it happens in all the cells, but to a greater extent organ wise, it happens in the GIT and the renal system also. Then the glandular secretions of various glands which are being synthesized and secreted out from the organelles into the cell cytoplasm, and ultimately from the cytoplasm into the cell, may also require certain energy processes. So this energy consumption which is there required in the synthesis of these glandular secretions is also coming from the ATP. Then lastly, we will find that the nerve energy, nerve conduction, energy for the generation of impulses and the transmission of the impulses from one point to the another point is also by means of active ion transport, and the energy for this active ion transport is provided by means of the ATP which is present there. So nearly if you see, all these processes are requiring ATP, and this ATP is present in the cell and it has to be provided immediately whenever the need arises. And one of the phosphocreatinine which is present there in the cellular level, especially in the muscle level, is the ATP storage in the form of creatinine. Now this is basically a biochemistry thing where you will see that how the carbohydrates are converted into the glucose. Glucose is broken down into glucose 6-phosphate or through glycogen. When glycogen gets converted into that glucose 6-phosphate, you will find 3 ATP molecules being generated. So glycogen getting converted on this side will show 3 ATP molecules, whereas here if you see directly glucose getting converted, there is a net ATP generations. The other thing is that there is an amino acid also which is present. We have seen the carbohydrates, and then we have amino acids. The amino acids also gets converted into the pyruvate. When the pyruvate is getting converted into acetyl-CoA, then we get ATP from there. Or the fats can be used which is present in the cell to get converted into acetyl-CoA, and that citric acid cycle is being used. So basically if you see this, the energy to generate the ATP within the cell comes from 3 basic sources, that is the carbohydrates, amino acids and fats. Now only among these three substrates which are generating ATP, it is only the carbohydrates which can generate ATP anaerobically. That means that without the utilization of oxygen or in the absence of oxygen also, the carbohydrates can generate ATP. Whereas amino acids and fats will also require, can generate ATP, but they will require the presence of oxygen to get ATP. Now this is the thing which is being used, where you will find that the oxidation of carbohydrates can occur at the cellular level in the cells, whereas these amino acids oxidation can happen within the mitochondria to generate the ATP, and the fats can break down within the can get broken down into the citric acid cycle in the presence of oxygen within the cell cytoplasm. So basically, whenever there is a sudden burst of energy which is required, there at that time, even in the absence of oxygen, it is the carbohydrates which can provide energy to the body. If this requirement of energy is sustained for a prolonged period of time, then from the carbohydrates it is the amino acids and the fats which can generate, utilize oxygen, and after utilizing of that oxygen you will require the energy to be produced. The difference here is, if there is a short burst of activity, you can have carbohydrates, but that is for a short duration of time. But when the energy requirement is for a prolonged period of time, the carbohydrates may not be able to sustain this generation of ATP for a prolonged period of time. Then it is the amino acids and the fats which will be taken up, and in the presence of oxygen to give energy. Now when we see that there is a sudden strenuous burst of activity happening, how is the energy levels utilized? So first, whatever is present in the muscle cell, it is the ATP. The ATP is broken down. This ATP present in the muscle cells, or whatever is stored in the cell or present readily available, will be utilized to generate energy and to provide that muscle contraction. So the first source of energy which comes within an exercise is from the stored ATP. This ATP which is present there may provide energy for a few seconds. Once that gets exhausted and the requirement continues to be there, or the muscle activity is going on, then the next thing which will be there which can generate is the phosphocreatinine, where the creatinine is broken down into phosphate. Phosphocreatinine is broken down into phosphate and creatinine, and then this will provide energy for a short period of time. But once the duration of exercise is still more prolonged, then it is aerobically generated energy which can be there, which has to be there, and this aerobically generated can come little later. But before that, these three substances which are present will be utilized. One, the already stored ATP. Second, the phosphocreatinine, which is also already present. And third, anaerobically, you will find that glycogen is converted into glucose, and glucose is getting converted into lactic acid. So for a few seconds, you will find that the glycogen is continuing to break down and provide 3 ATP, which 1 mole of glycogen broken down into glycogen, glucose and lactic acid. But at the end of this, what happens is, since it's an anaerobic thing, in the absence of oxygen it is happening, there is an accumulation of lactic acid which is happening, and once the exercise activity is over, this lactate is again oxidized to pyruvate and 80% is converted back into the glucose. Especially this happens in the liver, and the rest of it goes into the TCA cycle. So remember this point, with accumulation of lactic acid anaerobically, there is a accumulation going on of lactic acid. This lactic acid ultimately may be the responsible for the cause of fatigue, but once the exercise activity is over, this lactic acid does not go waste, it is getting converted back into glucose. 80% of it gets converted into glucose and the rest goes into the TCA cycle. So now we convert here back that what is oxygen debt. Now here we see that when a person is doing certain exercise, in the last class of sports physiology, when I was talking, I had said that there is exercise activity going on, there is an oxygen required. This oxygen requirement can be increased by increasing the pulmonary ventilation. It can also be increased by deep breathing and taking in more air so that more oxygen goes in. Once the pulmonary ventilation is increased in a trained athlete, this oxygen is carried to the muscle mass, and there the oxygen is transported into the muscle cell where the oxygen extraction is more. Now, as long as this oxygen extraction is taking place in a trained athlete, we have got oxygen which is coming and energy for sustained contraction is happening. But in that interim period where there is normally the energy is provided in the absence of oxygen, where you find that glycogen is getting converted into lactic acid, there to convert back this lactic acid into that glucose, that oxygen has to be replaced. Now, so this oxygen which has been utilized during the exercise has to be given back to the body once the exercise is over, and that is called as the oxygen debt. So oxygen debt is the amount of oxygen which has to be consumed, which is taken up by the body after the activity is over, to replace it back into its original status. So where is this oxygen needed? So once the oxygen exercise is over, we find that the person continues to hyperventilate or deep breathe, or the respiratory rate is a little more for a couple of minutes to couple of hours. It is not exactly hours. In a trained athlete it will be only for a few minutes. So what is this oxygen? Why is that oxygen needed once the exercise is over? The reason being that he has to clear off that oxygen debt. Now what is that oxygen debt? Where is that oxygen going? So the first thing is that extra oxygen is needed to convert the lactic acid which is accumulated back into glucose. So there ATP is needed to convert this pyruvate to oxaloacetate and later on back to glucose. So one reaction where the oxygen is needed and is covered up by oxygen debt after the exercise is to reconvert the lactate back into glucose. The second is, during this exercise bout, we have used the body has used the ATP and is broken down the ATP into ADP, AMP, and to release the phosphate bonds. Now whatever this ATP and how many ever moles of ATP has been used, that ATP has to be resynthesized. So to resynthesize that ATP back back to the normal levels, oxygen will be needed. Third, the phosphocreatinine was broken down in anaerobic contraction initially for a few minutes during the early bout of exercise to provide energy. So there the phosphocreatinine breaks down into a phosphate bond and simple creatinine, and that gives certain energy. Now that phosphocreatinine which was used during the exercise also has to get replaced, and that also requires oxygen. So converting back the creatinine to phosphocreatinine to replenish the quantities of phosphocreatinine back to normal, oxygen is needed. Thirdly, also the oxygen is provided by the hemoglobin during the exercise. We know that during exercise there is an increase in the oxygen supply through the capillaries. There is an increased myoglobin. The myoglobin also releases certain amount of oxygen. So there is a oxygen which has been utilized and the hemoglobin has been desaturated. So to bring back to resaturate the hemoglobin, or to bring back the oxygen content of the hemoglobin back to normal, or to bring back the oxygen content of the myoglobin back to normal, an extra oxygen will be needed. So that is another reaction where the oxygen has to be needed. And lastly, to re-establish the normal oxygen levels. When we are breathing in, there is a hyperventilation, the oxygen extraction has been increased. When the oxygen extraction has been increased during that exercise period, for whatever amount of duration the exercise has been done, this oxygen extraction is more, so the PO2 levels may fall. Now once the exercise is over, this PO2 levels has to be brought back to normal, and that happens after exercise during rest. So this is how the oxygen debt is needed. The oxygen debt is nothing but the extra amount of oxygen that a person has to breathe after a physical activity or a bout of exercise is over, so that the oxygen is utilized to replenish the chemical substances back to normal. And what are those chemical substances which needs to be brought back to normal? One, in the conversion of the lactic acid back to glucose. One, second, it is the converting back or replenishing the cells with the ATP. Third, replenishing the cells with the original levels of the phosphocreatinine. For that, creatinine has to be creatinine has to be converted to phosphocreatine. Second, the oxygen has to be replaced in the normal oxyhemoglobin level, or to bring down the oxygen, to bring back the oxygen levels back to normal in myoglobin, and to re-establish the PO2 levels. And this happens during the post-exercise resting stage. So I hope it is clear what is oxygen debt, how this oxygen debt is happening, and what is the need for the oxygen to be replaced after the bout of exercise is over. Now basically this all also affects indirectly the metabolic rate. So in biochemistry they would have taught you what is BMR, that is the basal metabolic rate. So whenever there is a resting condition where the person is absolutely resting for about 12 hours with 8 hours adequate sleep, no physical activity, no consumption of foodstuffs within the last 8 to 12 hours. In such a condition, if you measure the metabolic rate, that is called as the basal metabolic rate. So whenever any of these physical processes are taking place, then the physical BMR gets increased. So how do you measure the metabolic rate? The metabolic rate can be measured by direct calorimetry or indirect calorimetry. Now, what is direct calorimetry? If you remember, we had said that whenever there is a physical activity going up or certain metabolic activity increasing, the energy is used up by the body, and ultimately this energy is converted into a heat. If you measure the amount of heat output, it will give you an idea of the metabolic rate of the body. So it is a very difficult process to measure and is not a standard measurement, but it is an indirect way of assessing the basal metabolic rate. Whenever there is an increase in the heat in the body temperature temporarily may increase. That itself, the body will appear warm, and that means that some basal metabolic rate activity has gone up. So increased heat production in the body is an indirect assessment that the BMR is increased. The indirect calorimetry measures the rate of oxygen usage by measuring the amount of oxygen used in the inspired air. So here it is all biochemistry, where they would have told you 1 liter of oxygen yields about 4.8 calories on an average diet. So by measuring this, you can also measure the basal metabolic rate. So what are the conditions for measuring the basal metabolic rate? A person has to have a 12 hours fasting. He or she should not have done exercise. There should be a constant temperature, no fever. There should be no mental excitement or no any other stimulation should be given either in the form of caffeine or any other medication taken. And one more thing apart from this is that there should be a good amount of sleep taken for the previous 8 hours to measure the basal metabolic rate. Now, let us discuss from the physiological point of view what are the factors which are increasing the basal metabolic rate. The one factor which basically increases the basal metabolic rate is exercise or any physical activity. Say for example, even if you are standing in your dissection hall or you are standing for a long period of time, it will raise the basal metabolic rate. Sitting for a long period of time also involves certain muscle contractions where the muscles of the back are keeping your body straight against gravity. So some physical activity is going on. Working on a system where they say that nowadays the culture is work from home, the software people working from home, they say that we are at home, we are simply doing work on the system. No, but that is not a complete rest. That also involves certain physical activity which can raise the metabolic rate. And exercise, whether mild, moderate, severe, will definitely raise the basal metabolic rate. Another activity which will raise the BMR of the body is eating. Persons who are habitual of eating every 2 hours, every 3 hours instead of having a breakfast, lunch and a dinner, if you go on eating regularly, that also will make the BMR to increase. Basically by two things. One, if you are consuming regularly, eating every 2-3 hours, and that snack which you are taking contains protein, that itself will increase the breakdown of the protein will increase the BMR because they generate or result in high calories. So first, the heat products of the body, the heating mechanism is increased, more amount of heat is produced, BMR is increased. Plus, when you constantly go on eating after every 2 hourly or 3 hourly, you are stimulating the GI tract. There is a GI activity going on. GI tract is nothing but, especially the stomach and the intestines, are nothing but smooth muscles. So constantly a churning or smooth muscle contractions is going on in the stomach. That itself will increase the activity within the body. So smooth muscle activity is increased by regular intake of meals, and that increases the basal metabolic rate. Even a lean muscle mass or a lean body mass, where you have got a higher muscle ratio to a fat ratio, also increases the BMR. The hormones which can be causing an increase in the BMR is basically the thyroid hormone, the growth hormone and the testosterone. This we have discussed in detail, but to come to briefly around, we know that the thyroid hormone, especially the T3 and the T4, will act on the cells. When they act on the cells, they will increase the enzymatic processes in the body. So when the enzymatic processes are increased in each cell, so there is an increase in the metabolic rate. So this is how a clinical diagnosis of hyper or hypothyroidism can be made, where in a deficiency of thyroid hormone, hypothyroid, all the cellular processes are reduced. When the cellular processes are reduced, the basal metabolic rate is increased. When the basal metabolic rate is increased, you will find that the heat produced also is reduced, and when the heat produced is reduced, the person will complain of excessive cold. On the other hand side, in a hyperthyroid person, you will find that there is excess T3, T4. This increased T3, T4 activity will cause no doubt catabolism of the foodstuffs and produce more heat. Plus, this thyroid hormone, excess thyroid hormone, will cause increased cellular activity. It will stimulate the increased enzymatic processes within the cell. All the basic cellular activity will be increased. When the basic cellular mechanisms of each cells are increased, there is an increased heat production in the body. So this increased heat production in the body will cause the person to feel very warm. In summer, they will feel more warmer or more hotter than compared to a normal person. In winter also, to an extent that they may complain of feeling warmth. So this is the how the thyroid hormones affect the BMR. A decrease causing decreased BMR, increased thyroxine hormone causing increased BMR. So also we will see another important hormone that affects the basal metabolic rate is the testosterone. The testosterone is gradually increasing in as a person or the child turns from a child to adolescence. So during adolescence there is increased testosterone secretion. This increased testosterone secretion is again causing increased production of heat in the body because of the increased activity, cellular activity. Hence you will find that when you touch a young person or young boys, you will find their body having little warm. A little more warm than others is because of the additional effect of testosterone on the cellular activity causing increased heat production. Then growth hormone. A growth hormone is necessary for the basic level of BMR to happen. If there is no growth hormone, the BMR is reduced and the cellular processes are reduced. So basically 3 hormones, thyroid hormone, growth hormone, testosterone affecting the body BMR. Then sympathetic system. Now this sympathetic system, whenever there is a sympathetic stimulation, there is an increased epinephrine, norepinephrine, adrenaline. This all will cause an increase in the cellular activity. Increased cellular activity again means increased BMR, increased breakdown of fats, carbohydrates and proteins, increased generation of phosphate molecules and increased heat production in the body. Plus breakdown of the brown fat will also happen excessively, so the BMR is increased. The other factor which will increase the BMR but not normal is fever. So what is fever? Fever is nothing but an increase in the body temperature. The raised body temperature will stimulate the cellular activity. We know that there is some basic activity happening in the cells. Whenever that body temperature increases, because of the increased temperature, the enzymatic activities increase. So whatever metabolic processes are happening in each of the cell will be enhanced and will happen at a higher rate, at a faster rate. So in fever, the metabolic processes, the cellular processes, the enzymatic processes are increased. So there is an increase in the basal metabolic rate. Then in cold climate, this is especially seen in extreme cold conditions where you will find that to protect the body against the increased cold environmental climate, the body tries to produce more amount of heat. So for increased heat generation, there will be an increase in the BMR activity. So in such people, you will find that basically it is a correlation with thyroid hormone. You will find that not only T3, T4 is increased, but you will find that there is an increased secretion of thyrotropin secretion hormone also. Where TSH levels are more, TSH's level is controlled by T-thyrotropin there. So all these hormones are increased. So in cold climate, the basal metabolic rate is increased to keep or protect the body against the extreme cold conditions outside. Then this is another thing where you will find that a small body size will have a raised metabolic rate. Where because the surface area to the volume ratio with decreased size causes increased loss. Now this is not usually seen in human beings, but when you compare in the animal world with the small animals, rat versus an elephant, it is something like that, where there is an increased surface area to volume ratio, a decreased size will cause increased heat loss. So a small body size will cause an increase in the BMR. Now just to see here, where are the processes or where is this energy used? We know that even at resting conditions, certain heat is produced, which is nothing but the basal metabolic rate. So where is the energy used here? So if you see this diagram, you will find that basically most of the energy which is being used, the daily energy usage, which is being generated is to maintain the BMR, normal BMR. So to maintain the normal activity in the body. And what do you mean by normal activity in the body? It is the normal breaking down of the carbohydrates, proteins and fats, so that the basic processes go on, basic enzymatic reactions takes place, and for that 60% of the energy is used. A part of the metabolic rate is also reduced to certain extent but utilized during the sleeping metabolic rate. No doubt the better BMR during activity period is less than the sleeping period, but some amount of energy is also utilized to carry on the activities during sleep. Whereas you will find that some amount of it is used in the arousal mechanisms. So all this contributes, whether you are in arousal state, the BMR is activity is going on, whether you are in a sleeping state, still the BMR is there but to a lesser extent, but still that utilizes energy. So majority of the energy is used to keep the body condition within the normal limits. A part of it is used to cause the thermic effects of food, that is the heat which is generated in the body during the food process is somewhere around 8%. Non-exercise activity like simply sitting down or simply standing or simply lying down, that also is an exercise in the body, and that also utilizes energy to the extent of 7% of the total energy is used in a non-exercise activity. Then 25% is in some purposeful physical activity where energy is used, where you are doing some physical activity. About 25% is 25% of the energy is used for that purposeful physical activity. Now where is the energy stored? This is the storehouse where you find that glucose is there, glycogen is there, protein is there, fat is there. So you can find that 20 grams free glucose, or if you have in the body 20 grams of glucose, it is sufficient for 1 hour of energy process. Whereas in glycogen in the liver, 100 grams in the liver is stored and around 200 grams is stored in the muscle mass. 10 to 12 kgs of protein is present in the body, but little is used because basically it is the carbohydrates which are coming into the picture. Either the glucose directly or the glycogen breaking down into the glucose is supplying the energy for the body. Proteins are kept as reserve, and then another is the fat. 250 grams of triglycerides when it burns gives around 2000 calories or 2 kilocalories. 10 kgs of fat could last for around 40 days. In other words, the BMR of a person who is doing no activity at all, but in the simply lying down with minimal physical activity, requires around 1600 to 1800 calories per day. So that is being supplied by means of only glucose or glycogen. Any excess of activity above that 1600 calories or 1800 calories would involve the proteins and the fats. Now this is another job, this is another thing where it is for you to think over it, where in France who are riders will require around 10,000 calories per day. Apart from requiring or burning out with that riders 10,000 calories per day, they still lose 4 to 7 pounds in a 3-week race. So what is that? How is that they are burning out the calories, and how does our body decides whether it requires to burn off the calories or to store the calories is your task for the day. Now basically it is again biochemistry where you have that the glucose and fatty acid cycle, it becomes a reversion, it becomes a revision. Adipose tissue is always undergoing lipolysis where the fats are being used, thus liberating the free fatty acids. Triglycerides also provides the free fatty acids. Adipose tissue is always synthesizing the triglycerides which are reesterified to glycerol. But this glycerol is again needed to make triglycerides, and it must come from the process of glycolysis. Therefore, it cannot reuse the glycerol which is being generated. Therefore, for using glucose for energy, whenever there is a glucose used for energy, it leads to the fat storage. Fat usage for energy leads to the glucose storage. So this is about the glucose fatty acid cycle. Now again, the hormones which are involved in the control of the free fatty acid production. Here if you see the glucose undergoing glycolysis and it is causing the production of glycerol. Glycerol combining with fatty acids to form triglycerides. Triglycerides breaking down into fatty acids. Fatty acids breaking down into free fatty acids. So now being liberated into smaller free fatty acids. So what are the hormones which are affecting? If you see that this conversion of triglycerides to free fatty acids requires the hormone sensitive lipase. This hormone sensitive lipase will trigger up this reaction. For this reaction you require cyclic AMP, and the hormones which are promoting this cyclic AMP is epinephrine, thyroid hormone, cortisol and growth hormone. So all these four hormones will cause increased production of cyclic AMP. This cyclic AMP will stimulate the hormone sensitive lipase. It will break down these triglycerides into fatty acids. Whereas on the other hand, if you see this reaction here, glucose being converted into glycerol, insulin is one which promotes, whereas the other thing, cortisol and growth hormone, are negatively acting on it. Similarly, the control of glucose usage by the fatty acids. What is this here? It means that the low glucose starts the utilization of glycogen there, but allowing the lipolysis and re-esterification of free fatty acids. The free fatty acids and the ketones supplied to the muscle increases the production of acetyl-CoA from these substrates. In resting condition, this process exceeds the need, so there is a buildup of taking place. Now control of blood glucose from a physiological point of view, here you will say that this is the blood glucose level, here the liver is producing the glucose. So there is a glucose production which is happening in the liver. This glucose production is increasing the blood glucose level. On the other hand, this excess blood glucose which is present is taken up by the muscle and the adipose tissue. So what are the hormones which are affecting the glucose production or the uptake by the muscles and the adipose tissue? Basically, if you see the role of the insulin, what does insulin does? Insulin basically sees to it that there is an increased uptake of blood glucose by the muscle and the adipose tissue and its usage. Whereas on the other hand, the same insulin acting on the liver will decrease the glucose production. Whereas there are certain anti-insulin hormones where you have got epinephrine and glucagon. All these two hormones will act directly, causing increase in the glucose production and increase in the liver glucose production, causing increased blood glucose. So basically, if you see, epinephrine and glucagon act on one aspect of this where they are causing an increase in the glucose production in the liver. Whereas if you see the cortisol is having influence on both sides. At the production level, it is increasing the liver glucose levels, whereas acting on the muscle and the adipose tissue, it decreases their uptake. So here cortisol, a dual role acting on the production where it increases the production, whereas acting on the muscle and the adipose tissue, it inhibits it. Whereas growth hormone exclusively acts just by reducing the uptake or utilization of glucose by the muscles and the adipose tissue. So this is in summary where we have explained the hormones, what is the role of the hormones on the free fatty acids through the glucose and on the fatty acids here. And on the next slide we have explained about the control of the blood glucose where various hormones are present, how they influence the blood glucose level either by increasing the production or by increasing their uptake. That is the role of insulin. All other hormones are having action of exactly opposite to insulin. Thank you. With this we end our class on energetics and BMR. We will meet again on Monday, where on Monday we will discuss about ECG.